So this is an example problem. It actually is based on problem 25 in section 5 of chapter 9 of ZIL. But this is just an example of using the gradient operator in an extended problem, but not a very difficult problem at all. This is actually one part of one problem on the 2276 midterm from 2025. So this is an exam relevant kind of problem. It's a very short one, a very simple one, but it'd be probably worth maybe 10% of the exam as an example. Okay? So the problem statement, and this is what you'd be given on the exam, is what we have written on the board here. So it says, find a unit vector that gives the direction in which the given function, which is over there, increases most rapidly at the indicated point, and find the maximum rate of change of the function along that direction. So before we, and we're given this function, f of x, y, z is x squared plus 4xz plus 2yz squared, and the point of interest is 1, 2, minus 1. So let's just stop for a second before we rush into this. The function we're given is a scalar function, as it should be, because we're going to calculate the gradient of that, and we only calculate gradients of scalar functions. The result of the gradient operator is going to be a vector field. So it's a vector that is a function, each component of which is a function of x, y, z. That's what we expect to get. So we start with the scalar, we're going to get a vector field, okay? And that vector field is the gradient of the function, okay? That gradient tells us the direction and magnitude of the rate of change of f at any given point along all possible directions. We're asked to find a unit vector that gives the direction in which the given function increases most rapidly at the indicated point. So what that means is we're going to calculate the gradient in general of this function. Then we're going to evaluate that gradient at the given point, 1, 2, 1. And as a result of that, we're going to have a fixed vector, not a vector function, just a vector as a set of 3 numbers. And then we're going to calculate a unit vector along that direction by normalizing that. Okay, so that's the elements of the problem. So the first thing we're going to do, right, is calculate the gradient of this f. Okay, so the gradient of f in general, right, f, and it's not vector f, it's the gradient of f. Okay, that is the derivative of f with respect to x, I, plus the derivative of f with respect to y, j, plus the derivative of f with respect to z, k. That's the general gradient operation. Okay. Now, this one's simple enough that we can probably just do this in our heads and calculate each component as we assemble the gradient. That's easy. If this problem were a lot more complicated, we'd probably calculate each of these partials separately as a separate line in our solution and then combine them. But this one's simple enough that we can just sort of go ahead and do this. So the derivative of this entire function, not just the first term, but the entire thing, right, with respect to x. So that's 2x plus 4z, and then this doesn't depend on x, so that has 0 dependence. So it'd be 2x plus 4z, and that whole thing is along the unit vector I. And then we take the partial, that entire function, not just the second term, right, the entire thing, with respect to y. Now there's no y dependence, linear dependence in y, so this is 2z squared, j, okay? And then finally, we ask the derivative with respect to z, okay? Again, the whole thing, not just the last term. The fact that this has 3 terms is just, has nothing to do with anything. That's just what the function happens to look like here, okay? But I've seen that mistake made before. So we take the derivative of the whole thing with respect to z. So no z dependence, linear z, quadratic z. So we got plus 4x plus 4yz. And that's along k. Okay? It would be an error, it'd be a mistake to not have these unit vectors here at this point, right? To just have 2x plus 4z plus 2z squared plus 4x, that would not be right? This has to be a vector field, and each component is specific to that partial. Okay? So you have to have this perfectly right on an exam situation or any real situation in real life. Okay? So this gives us, for any x, y, z, the vector along which the original function varies most rapidly, right? And also the rate at which it varies. So now what we're supposed to do is look at this. We want this gradient at this point. That's what the question's asking about. So we'll solve x equals 1, y equals 2, z equals minus 1. So if we say the gradient of f at 1, 2, minus 1, and that's how you would write that. Okay. So that would become, all right, well, 2 minus 4i plus 2z squared, so that becomes 2j plus 4x is, 4x is 4 plus 4 plus 4y times z, so 2, so it becomes minus 2. Okay. So this whole thing becomes minus 4. So this becomes minus 2i plus 2j minus 4k. That is the actual vector itself at this point. So it's the gradient of the function at this point. So you see, it's not a function of x and y anymore, it's just a single direction. Okay. Now let me just erase this and continue on over here. Okay. Now, the problem said, I just erased it, the problem said, find the maximum rate of change of the function at this point. So this is a vector describing the rate, the direction along which the thing varies most rapidly, but the rate at which it varies is the magnitude of this. So the magnitude of the gradient at this point, right, is, okay, well, it's just the square root of the sum of squares. So minus 2, so it's 4 plus 2, 4 plus 16, right? So that's square root 24. Okay, so we can write that as, 2 square root 6. Okay? If this were a normal engineering problem and we had units associated with this, then this thing would have those units per meter. Okay? But right now we're just in sort of pure calculus land, so this is considered unitless now. But this is the rate at which the function is varying along this direction. So we're almost done the problem. The last part of the problem was just that, actually was said first, is we want a unit vector along which, along this parallel to the direction along which the function is varying most rapidly. So this is the direction along which it's varying most rapidly. This is the magnitude of that gradient. So the unit vector would be this vector divided by its magnitude. So if we say n hat, and normally we'll use this as a normal, but we'll just call this vector n, is, well, it's minus 2i plus 2j minus 4k divided by the magnitude of that vector. And that is a unit vector. Now, normally you would simplify this down, especially since it's obvious. We're 2, 2, 2, 2, 2. So this would become 1 over square root 6, and then I'd have minus I plus j minus 2k. Okay. This vector here is a unit vector pointing along the direction at which this function varies most rapidly at this point. Okay. That's the entire problem. Okay. The errors you can make in this is to not use proper vector notation, to add these up incorrectly, not to insert the actual specific point here to calculate the gradient at a specific point, and then maybe to not normalize this vector. I suppose those would be the most common mistakes. So this would probably be about as easy a part of the midterm as you could get. The next, usually on a midterm, and this one's no exception, in another little quick module after this, I'll do the second part of this would be one problem. This is usually problem 1. The first part is a gradient. The second part would be to calculate a divergence of a curl. And that's just a very easy part of the exam before the later questions where we get into more difficult stuff.